talk seminar. My name is Jonathan Bowen, and tonight we've got Jung Act. He finds is at the NPL National Physical Laboratory. I'm interested to know where the practice are with mathematically structured programming.
That's the University of Strathclyde.
Yes, around the mathematically structured program. But I mean, it's always interesting to see it in English where so he's going to be collaborating with the University of Strathclyde. He might be at the university.
It's complicated.
It's complicated. Yeah. Okay. Keith is going to explain the complications. Keith is collaborating with the Strathclyde and then to the second speaker. And he's going to be talking about functional programming and dependent types for meteorology. Oh, sorry, metrology, not meteorology.
It's not the weather, no.
Although he's got a very nice picture with clouds there and a beautiful. I don't think it's going to be anything on weather. If I'm correct.
Unfortunately not. No. That's the metal.
And he's been at the NPL for 34 years, which is quite a while. I think he joined just after Alan Shoring left. Right. Is that correct? So, but he's been there a while. He says he collaborates with scientists and administrators.
Yes.
He can tell us which you enjoy most. And good. Well done for trying to combine the two. I'll also say that although I'm chair this year, he is the vice chair. So this is a sort of an inaugural lecture for FACS because he's going to take over as chair from next year if all goes well. So I'll say thank you very much to him. And I'll maybe stay on helping him. But anyway, we've got a sort of transition at the moment between me and him. So hopefully this is a little introduction to Keith, because he's going to be in charge from next year. So.
Okay, thank you, Jonathan. So we'll be talking about some functional programming and dependent types and some work, as I say, that NPL's been doing jointly with the University of Strathclyde. Here's the agenda for the evening. So I'll just talk a little about what I'm hoping to get over with this talk, some introductions, some background information. We'll then look at some case studies. Nothing too complicated, but just generally giving some sort of an overview and conclusions. So, what are we seeking to do with this talk this evening? Well, present an overview of the work, really, and also present a case for the value of, the knowledge of theoretical computer science and functional programming and those sorts of topics. And I think it's important that people who code and people who work in IT know about these things and have an appreciation of them. And certainly we're trying to pitch this to within the department to make sure, because these subjects are important. And also some feedback from yourselves, some ideas. You guys are the experts in the fields, always welcome. Well, there we are. National Physical Laboratory, it's the UK's national metrology, metrology being the science of measurement. Founded 125 years ago this year, so we've all got all sorts of things going on to celebrate our 125th anniversary, including an open day. So if you want to come along and see the place, that's you're very welcome to. Just go to that link.
What day is the open day?
Good question. I'm so sorry.
That's okay.
It's via the link, and you will need to book in advance. I should have anticipated that question. Yeah. Right.
By the way, he says he's not taking questions during the talk.
Yeah, we'll see. Yeah. Okay, so there we are. Our headquarters is in Teddington, but a sort of newish innovation is that we now have locations in Strathclyde, Surrey and Cambridge. Field and Solihull. For data science, it's mainly Strathclyde, Surrey and Cambridge, where we have staff who are based there. And again, we're with part of the Department of, oh my goodness, the DSIT. Oh, sorry, that's terrible. Mine's got a blank, and this is getting recorded on YouTube as well. That's terrible. Right. Please do. Department of Science, Innovation and Technology, my goodness. So 800 scientists, it says on this slide. I think it's more than that these days. There's certainly well over 1,000 staff, so I'm sure that number is higher. Right, so important to MPL is that we address the national challenges. Look at prosperity, security and resilience, environment and health. So it's a key part of what we do. And it's data and digitising data, and that's important for the data science. And of course, MPL has a long and very significant history in computing. I won't dwell too much on this, as spoken about this in other talks, and I'm sure this is stuff you may be familiar with. The pilot ace, Alan Turing, of course, Donald Davies, packet switching, lots of very important work, and taking forward is still really the data science department is very much the successor of the mathematics department. Of course, first employee was this chap here, who needs no introduction. Michelle Mood. I still don't know what that race is or what he was. Yeah. Right. Okay. So the aim of the department: confidence in intelligent and effective use of data. So we're a mix of mathematicians, data scientists, AI, machine learning. That's a very big thing these days. Statisticians and physicists. So there we are. And this is a relatively new thing that we've got. Graduate scientist scheme. We're recruiting. We have a special training course for graduates who join us, and this is kind of one of the things I got in the back of my mind with introducing formal methods, theoretical computer science, functional programming. I think it's important this sort of stuff is put over. With collaboration. And also, as we're talking at the British Computer Society, the Alliance for Data Science and Alliance for Data Science Professionals. That is quite a significant development in which MPL and BCS have collaborated. So almost like certifying data scientists, certification thing for data scientists. I think a couple of years ago. Significant. So, okay. Right. So what are we all about? What's this all about, really? Well, in terms of, it's about fruitful collaboration between metrologists, measurement scientists, and computer scientists, trying to get sort of communicate fruitful ideas and just taking the whole computing and how it can be used in the context of metrology and taking it forward. And of course, this is nothing new. I'll put a link there to a talk I gave a few years ago, going back to Turing, and also Christopher Strachey, MPL's support of his work and his sponsoring, and a lot of things. Algol, the work on developing Algol proved very significant to MPL. Okay, right. So our cooperation with Pride. It was a project Trust to the Fore. It was engagement in the structured programming group with some joint appointments: Conor McBride, Frederick Norville-Hosberg, and then the head of department, Neil, who is now retired, and a couple of PhD students, Andre Eigel. Been doing a lot of work with this closely. So that's really what it's all about. And there we are. So a couple of BCS presentations have been given previously by Frederick, Conor, and Andre. So they are up there on the YouTube, on the BCS YouTube channel, to provide some further context about tonight. But again, Project Trust to the Fore is all about trustworthy software, looking at how we can bring some of this theory in type systems, how we can make metrology software more reliable. And, you know, so they publish papers that are full of things that look like that, which can be a little bit alarming. People who are not necessarily specialists in this area, but what does this sort of stuff mean? Is it worthwhile for MPL to have people who can sort of understand these, use them? Is it relevant to developing trustworthy software tools? I would say it is, but it is about putting the case for it. Yes, many other things published as well. Okay, like any good National Metrology Institute employee, I must of course reach for a standard when using these terms. So there we are, there's a British standard. It addresses safety, reliability, availability, resilience, and security issues. And there are facets of trustworthiness. So that's really where I'm, what MPL's coming from as far as defining the term. But going into detail about that is a discussion for another. Right, bit of background information. Theoretical computer science. Okay, you guys are all experts. Let's see if we can agree on a definition of what it is. And if anyone disagrees, you can say so. So MPL, you know, follow the funding, and there's UK Research and Innovations. Fundamental and foundational aspects of computers and computation. But some might object to the term computers. Is this purely computation? Abstract exercise. What are your thoughts? And there we are, inevitably Wikipedia. So this is the various subjects. Ontologies. Working ontologies is important for MPL. And indeed, last year, my colleague Jean-Laurent Nicolette gave an excellent talk looking at some of the work that MPL is doing in ontologies, and also a secondment he was doing with the International Bureau of Weights and Measures, which is the body that defines the SI system, which you may well know, and for creating a digital framework and the ontologies in that. And that's all up there on the BCS YouTube channel. There we are. That's one of the things we're going to be looking at this evening. Okay, so what kind of underlines, what's really the motive, one of the motivations for this work? Well, we're going to Landon, another one of our BCS FACS important people, heroes, exactly. Yes, absolutely. Absolutely the right word. And so we look at his absolutely seminal paper, The Next 700 Programming Languages, which you haven't read, please do, because it is an important paper. And there he raises the point. Lisp brought a class of entities that are denoted by right, nearer to those that arise in models of physical systems and in mathematical and logical systems. Okay, so he was talking about Lisp. Does this apply to newer functional languages, like this quasi-functional? Well, let's think of it as a functional language. Does it apply to newer ones? That's cool. Idris 2, that sort of thing. So what we just wanted to do is just explore some of these ideas and see how some of this metrology software looks in some of them. I will assume knowledge amongst yourselves as to what functional languages are and that sort of thing. If we want to talk some more, I've got an appendix where I've kind of put how I'm trying to pitch this stuff. We can perhaps do that later if there's time, but I will work on the assumption. I just know what that means. Okay, let's look at an example where things like these dependent types that we'll be talking about. This is kind of the dream. This will be the ultimate goal. There we have a pretty typical sort of calculation that you're going to be looking at around here. This is for calibrating resistance values. What we have there is there's a matrix of measurements. To the right there, of left to the left, we have a matrix of measurements, each various dimensions. We'll talk about that in a minute. After equals, we have a row vector full of measured voltages. And so what it is, we need to calculate that series of parameters there from the measured voltages and the matrix. There's a series of time values. And the point being that this matrix, there's dimensions, there's units associated with them. So the dream, as far as say being able to use dependent types, is that supposing the type of those columns and the cells within the row vector of the times, it was, instead of it just being integer, at some combination of integers and units, say that each one of those types was a function. A function from, say, the column index to an appropriate combination of units and numeric values. For example, with the DC, with the Ds, the Ns, Cs, they're all just unit values. So that would just be 1. With the Ts, it will be time, but as I say, something that maps from the column index to the appropriate type. In other words, a type that depends on something that is not a type. And that it might take on what a dependent type is. Do filter chip in, Andre. Okay, so let's look at some of these case studies. We want the ones that are realistic, but not necessarily overly complicated. So that's really what we've gone for. So there's the selection of what we've looked at. So go straight to the law of propagation. Uncertainty. Let me stress that this is nothing to do with live software that's actually used by the scientists. It is in the sense that we're drawing these case studies from this software, but nothing we're looking at ultimately will be used for calibration or testing purposes, maybe for testing, maybe for validation and verification, but this is very much an academic evaluation. So let's look at uncertainties and look at it at least in terms of context of what the uncertainties mean in terms of measurements in MPL and the sort of bread and butter work that we do every single day. So there we have a value of a resistance value with an uncertainty given in parts per million. And so let me just these and then perhaps a bit more about that. So this is really where, because the true value is of a measurement is something that is impossible. It is a physical impossibility to find such a thing. What we do is we quote a value and then an uncertainty. In other words, the probability in which the true value will lie. And so typically you're looking at a normal distribution, standard uncertainty, standard deviation, subtleties going on there that I won't go into, but I certainly have colleagues who could tell you more about that sort of stuff than you ever realized you needed to know. In that, we can sort that out. Again, it's based on a normal distribution, it being that there is a 95% probability that the true value lies within two standard uncertainties of the value that is quoted there. And that is, of course, all being based on a normal distribution. Other distributions are available, but that requires other mathematics. So we need a means sometimes of combining these standard uncertainties to create perhaps one overall uncertainty. You might have an array of sensors feeding into your data, each with its own uncertainty. So we have the law of propagation of uncertainty, which, yes, is a pretty simple calculation, but nonetheless, it's an important one. So it proved a useful starting point. And that comes from a document called the Guide to the Expression of Uncertainty in Measurement. I've underlined expression because people get upset if you call it the Guide to Uncertainty in Measurement. Or the GUM. So there we are. This is the calculation that we're just going to be looking at and see how we can implement it in a variety of ways. And that's also a point I want to make. A measurement result is incomplete without a quantitative statement about the quality of the measured value in the form of an uncertainty. Hence, it's important, all right? It might seem like it is a straightforward calculation, but nonetheless, it's important to get these things right and think about them. So there we are. There's a MATLAB implementation. Almost two ways, almost like a traditional imperative approach. And then there's something that looks like a functional one. Then going back to Peter Landin's point, something that looks more like a mathematical statement in the loop at the top. There we are. So we looked at these, and then those are the outputs. Okay, in places. Okay, so let's have a look at this calculation in a number of functional languages, starting with, well, the Haskell package library, which provides matrix multiplication, transposing. And we have something here that more like a mathematical calculation. Then say the loops. So that is interesting. The F-map in the language. There we are. The point being is that really, if simple calculations like this are too much of a head scratcher and are just too difficult by anyone other than a non-specialist then it's sort of pretty much game over. But that proved to be the case, and there we are. That's just the up. I'm just showing that to prove it's same. So, okay, let's look at another approach using Haskell with a vector library that Andre wrote. So again, similar sort of thing, although this time the multiplication has been sort of overloaded, i.e. more than one use. It can now be used for vectors as well as normal scalar values. And we're summing them up and we're taking the square root, the value there. Okay, let's now look at Idris 2. And excitingly, we're using a colon rather than the two double colons, which the two colons, which seems to be a significant thing amongst experts in this field. There we are. And here's our first little bit of four. There was a vector that contains 4 doubles, a type that depends on something that is not a type, in this case, the number 4. And again, we've got something there that looks like an equation. Oh, there we are. No value, just doing that. Those the Haskell implementations will run on Windows. That was run on Linux. Okay, and finally, Python. And let's have a look again. Similar. This is again getting back to more traditional program. We've used NumPy library to declare that, but there's something a bit interesting going on here, which was pointed out by a colleague. We have a little bit of, just for neatness, we can use that assignment statements, make the C MP square, and that makes the code nice and neat. But there's even with this straightforward example, there is an issue here, isn't there? Because the C, it's almost like it's changing its identity, isn't it? Originally, it's just the value of sensitivity coefficients, and now it's also being used for sensitivity coefficients squared. Now, ideally, perhaps you should introduce a new value, C squared or C transpose or something like that. But the fact that you can do these sort of things and the numbers all work out, is that a problem? Is that something to be concerned about? I would suggest it is. But, the fact that you can do that sort of language, where with a function example, that was not there. So that was an interesting point. Okay, so moving on to our next example, we have a piece of software called GrabCalc, which is used to help make calculations necessary when creating gas mixtures. MPL has a gas reference materials standard. Using that gas references, it can be used for a variety of purposes, calibration of devices such as, for example, breathalyzers, or maybe pollution detectors or something like that. They need standard mixtures of gases which you can use for that purpose. And this
Can you hear anything now?
Yeah, I can ask, can you hear anything? Can hear, yes, they can hear.
Perfect.
Great, thank you.
Fantastic.
No.
What was the issue?
Oh, I'm not too sure. I just
They don't know what's wrong, but it's working now.
slide you on. So the other two.
Sorry?
You know what slide you're on?
Yeah.
Great, thanks very much.
Thank you.
It's not sharing though, is it?
Yes, no. You need some help from IT. Can you just get his slide?
Oh, there it is.
Great, thank you.
All right. Sorry about this. We are back. So to recap, the goal here is to show a different way of making writing software. And for this, we've taken existing specifications and implemented them in different sorts of software to see what benefits we would get from different kinds of programming languages. I've written this, well, I've designed this small graph that has two axes. The first one is, are we measurement dimension safe, which is, are we able to take into account errors in units of measurements? And are we matrix safe, which is, are we able to detect errors in the way we build our linear transformations? And the first tool that we looked at is the tool that everyone uses, is Python, which is not dimension safe and not matrix safe, because it cannot detect any errors ahead of time in terms of linear transformations or in terms of misuse of units. So we moved to the next tool that we had available that is quite easy to use, that is not Python, and it's F#, because F# already comes installed in essentially every Windows computer. And here you can see two programs, one of which, let me see if we can use this. One of which has, oh goodness, what is happening? Oh, never mind. There we go. One of them has this mole here saying that this array contains number that represent an amount of substance rather than a plain number. And this is already a win because it means that F# compared to Python is a lot more dimension safe. We can't detect errors to do with linear transformations or matrices, but we can detect errors with units of measurements, which is important if you're NPL. Now we looked at another programming language that's a little bit more difficult to use in terms of installation and ergonomics, but still has a lot of things going for it, which is Haskell. So here are three programs, all the same program, and I forgot to mention, this is only the type signature. The implementation for those is all the same, because in all cases we're doing the same component calculation for our gas mixture. So the first one, those brackets here indicate lists. So it takes two lists, a list of rational numbers, a list of gas components, and returns a list of rational numbers. That is not measurements, well, that is not measurement safe and that is not matrix safe. Those lists can be any sizes and the units could be anything. In the second case, we've done something a little bit more interesting, which is we've abstracted over the data representation. So instead of dealing with numbers, we're dealing with a number. It could be any representation. So in our case, it could represent doubles or arbitrary precision floats, arbitrary precision integers, multiple size of floating point values, or even uncertainties attached to the values. And that's interesting because now you can give semantics to your number without changing the logic. So you can choose what semantics to run your program in without changing the program. And finally, we've hard-coded specifically what units we expect to find in the data. So this one is an amount of substance, this one is an amount of substance, and this one is nothing specifically because it's a unitless value. So we've made some progress, and I've decided to. Why is this so slow? I've decided to put Haskell here because there are still some things we would want to do. So I've not shown this, but it's possible to make Haskell matrix safe, that is, ensure that the dimensions of our linear transformations match. And it's dimension safe insofar that we work with the framework that we have, but it's not super easy to use and it's not built in. It has many other trade-offs. The last tool that we looked at is Idris, which is a dependently typed programming language, which gives us great flexibility about what to write. And the program that you see here is the final version that we had, which was, can we make the program vector safe and dimension safe? And also we wanted to choose the data representation that we were working with. But not just that, we also want to make sure that we can change it if we want. So for example, if we're working with certain kinds of units, we want to work with feet and yards, or we're going to work with meters and seconds, we can change it. And this is what this does. This is abstracted over a graded number, which says the number is attached to metadata, and we have rules about how to compile or how to combine this metadata as we go along the computation. And this is what all those annotations with GR mean. And here you can see that we've kept around the matrix safe operation by using vectors, vect, which is not vectors in other programming languages, but is the size-aware list of Idris. And that brings us to here, where Idris is more, well, this specific example is more dimension safe than Haskell. We can more flexible. We can choose exactly what our numbers mean, what our dimensions mean, and what our grade means. It's not quite as matrix safe as in we could do better in terms of making it faster, making it easier to use, and making it more abstract over the data representation of vectors, but that is more implementation work that we have to do. So to conclude this small experiment with GraphCalc, what we found is something we somewhat already knew, but what is new is that we know how to apply it to metrology software, which is more types often means more safety, in that more often safety, that if you want to make sure that you remove a certain class of problems, you can. It gives you more expressivity because it makes more obvious what you're doing. If you're only modifying lists, it's not really telling you what you're doing with those lists. Whereas here we can say, well, those lists contains graded values. Those values are units, and those units combine in this specific way. And we found some interesting usability questions about what is the proper trade-off for a large company such as NPL that would be an appropriate trade-off between maximum level of safety and maximum level of expressivity and acceptable levels of usability, let's say. It's a question that is not answerable. It is mostly a cultural question, but it is still one that is interesting to bring up to people who are used to only leaving the top left corner of the graph that I've shown. We're moving on to we're moving on to the next case study, which was, can we make software in general better to write, easier to maintain, in a way that will essentially give more time to engineers to do their work rather than worry about developing internal tools. So here we have a piece of software that's written in LabVIEW that that helps with resistance calibration. And we thought maybe there's a way that we can do this, but better in some way by using new technologies that are unlocked by deep learning. So before we go there, we need to spend a bit time doing theory. I've had this nice Venn diagram here. And the reason for this is that what is going to follow is exactly at the intersection of type theory, category theory, and engineering. The piece of software is a piece of engineering. The theory that we're going to use is category theory. And the tool that is going to allow us to apply this category theory to engineering is type theory. And we're going to start with the specification of the problem. We have an application, and we want this application to communicate with some other system. So it's going to send a message. The message is going to be sent to a database, and the database is going to respond with a response saying, well, the message that you ask is this query, and the response to this query is this piece of data. Now, there is some more we can do with this. For example, this application can be part of a bigger application. And so what we were looking at was merely an intermediate layer of a larger system. that itself has messages and responses. What we can do is furthermore specify programs, or sorry, what we would like to do, specify programs that have multiple interfaces, multiple applications that interact with the same database or interact with the same lower level system. And just like before, we'd like to also compose or combine or add more programs on top of it. This is all again in the goal of simplifying writing software or making it easier to build software in a way that people can understand, maintain, and update. And one of the things we would like to do is to replace this interface above by something else. So for example, here we can imagine having a command line tool, and someday someone says, actually, we'd like to access this from the web. So you would like to make it a server, but keep the internals the same. The solution for this is what we call as Strathclyde containers, what mathematicians call polynomial functors. For our purposes, they're the same thing. What we really want is a rich algebraic structure. And so here I have shown 3 operations that we can do with containers. I will explain very quickly what they are. But essentially, you can add containers together, and what that means that you will choose between one or the other. You can multiply them with codes, which means you have both of them at once, or you can have them in sequence. So you have first container 1 and then container 2. And another construction that is very important is morphisms. You can translate or you can delegate from one container to another container. And where this becomes very important for us, again, let's remember the problem is that we have software. We want to make software easier to represent, easier to write, easier to maintain. Morphisms represent translations between systems that have requests and responses. So if a system takes in request number 1 and gives back response number 2, it can delegate request number 1 to request number 2, to a system that takes request number 2. And the subsystem will respond with a response number 2. And if we can translate back into response number 1, then we've done our job. This notion of delegating or mapping from one container to the other is very powerful, specifically given composition of containers. You can have a container C1 that delegates its work to C2, and C2 will delegate in turn its work to C3, and then C3 will compute a response, and then give it back to C2, and then give it back to C1. All this theory, and this is, by the way, this is where the category theory comes in, because category theory is essentially the study of compositional structures. We need to understand what it means to compose things together in order to understand how we can build larger systems. And the way we interpret containers in the context of software engineering is that containers are APIs. We have an input, which is the request that you expect to take in, and you have an output, which is the reply that we'll send back. And it's API in a very general sense, not just web APIs, but any kind of software interface can be represented as an input and according to this input, an output. And this last bit is actually very important because this is now where we have built the theory for our system. We need to now employ the tool to use it, which is type theory. And the container is given by, first we have S, which is the type of messages that your API will accept. And then you have P, which is the type of replies that you can give given a message S. So you need to know something about S in order to produce a reply that makes sense. And out of this, you can build a container with S messages and P replies. Now, this is very abstract. Like Keith was mentioning, we have all those, this is but one squiggle. We have many of those squiggles. What is really useful for us is the implementation as software. And this is, again, this is Idris code. And it shows the implementation of an API saying, first we have a message that's given by the type of messages, and we have a response that depending on what message we've got, we have another type. So this is the important part where dependent types become very important, and this is unimplementable in anything else, because you need to be able to write records or to write terms that have a type that changes depending on what value you've gotten beforehand. From this, we can build container morphisms, which are the delegating power of it. So this is saying if you have C1 and C2 two containers, this is how you forward messages to other messages and interpret responses to other responses. Again, there's a lot of squiggles, but the point is that the theory exists and is implementable in a way that we can run it as a program. And the last one, this one is composition. This is the thing that makes everything tick, which is if you have a morphism from A to B, another one from B to C, you can get, you can skip B and go from A straight to C. All right. Given this theory and given those tools, how do we relate back to our initial problem, which is, again, we're building software. We want to abstract over how to build software, abstract over common structures in software in order to build new features based on what we already know about this software. This is where our modal operations or our composition operation come in. So co-product for addition of containers says if you have one API, C1, another API, C2, if you add them together, it's like saying, well, as a system, you can choose to send me messages of C1 or messages of C2. And depending on what you've sent me, I will answer with an answer of C1 or an answer of C2. This is very basic, but again, you need just enough theory to write it down and just enough type systems to make it into a program. The second one, well, multiplication is, again, if you have two APIs and you multiply them together, it means that your system can accept two messages from, one message from C1, one message from C2 at the same time, and then respond with both responses at the same time. And sequential composition is very interesting because it allows you to define protocols within your APIs. So if you define, for example, a system that will say, first I need to call the database needs to reply with some data that I will then use to call either another system or another database or another web service. Then you will have to say, first do C1 with the answer of C1, send C2 with the answer of C2, give me the final result. And you can compose them infinitely. And finally, morphisms is delegation. So C1 can be implemented by delegating its work to C2. All right. What does this piece of software do? It has essentially three tasks. And that's what we're going to do. We're going to rebuild from what we know of this software, the theory that we need, or rather, we're going to use the theory that we need to rebuild the specification of this software. Its first task is to send measurements. So someone in the lab makes a measurement and they need to add it to the system. What do they have? They have a list of measurements. This list of measurements then forms a query that is then used against a database. The database receives the query with the list of measurements and then sends back a response. In general, if you're just adding something, it will be something like, yep, that worked. The second thing it needs to do is to analyze some data. So if you have a list of data that you've already measured and you want to build the final result out of it, in this case it's some statistical analysis, you take the ID of all your measurements, because they all share like a session ID. You build a query, this query is sent against the database will reply, everything went well. Again, we're just modifying something, we're not retrieving anything. And the last bit is certification, well, certify, which is I have all this data in a database and I would like to obtain something out of it, in this case a PDF, and I give it the session ID of the thing I've analyzed earlier. And again, translate the ID into a query the database responds with some data, we translate this data into a PDF, and then we record this on disk or in any way. So if we use the small boxes that we used before, we can translate those into, I'm going to say this is a container, so this is the message bit, and this is the response bit, and this is another container. And what we're doing is that we're creating a morphism between those two, saying the certify API will delegate its work to the database, and then this thing that turns around here says execute whatever content you've gotten. And you can do the same thing with measurements. So you can say the types of the ID doesn't change, but the type of the response, the type of the response changes. And once you have those three specifications, you can put them side by side together and look at them as an object. Again, we're not looking at the program, we're looking at the API of the program. So we're manipulating what the program looks like from the outside. And well, all of those interactions, we can say, well, those are all simply morphisms. So analyze delegates is stored to the database, measure all sold delegates to the database, certify all sold delegates to the database. Then we can use our operator to combine them, saying an overall program is essentially one of those three things. So we get to choose which one we call every time we interact with software. And for this, we're going to use a co-product, and we're going to merge everything to the database, and this arrow in the wrong side, but you can guess where it's going left to right. And because all of those three things are together, that's going to be our application. The application is one of those three interaction systems. And we can just write a small block for it. And now that we've abstracted essentially the entirety of our program into this small delegation process of here's the overall application and it interacts with the database. We can start manipulating this again as its own object and say, let's add more things to it. How about I put a server in front of it and then I can call it with HTTP requests? Or maybe I want to distribute a command line tool. So I merely need to add an interface that will read from the command line and print on the command line, and that will be the program that I'll distribute. The key thing is that the middle, look, everything that is after here, stays the same. So you don't need to worry about the details of implementation. The way the application has been advertised is enough for you to build two programs at once. And so we have a small prototype that does exactly this. You can see three instances of the same program. And the types here don't tell you much. It just tells you if you have a database instance, you can run it. Init merely puts dummy data in the database so we can use it. But then the rest is interesting because it says with the database that's been set up, run this HTTP server on localhost. And the implementation is given by this function here called plug front end. Not quite sure what it is yet, we'll see. For the REPL, it's the same thing. It says start a new REPL with this function. And for CLI says simply take inputs from the standard input and print out on the standard output. So what is this plug front end thing? What I'm going to quickly show you is that this is difficult to use. Actually, let me show you the next one. So the implementation of each one of those things, you notice they're all called HTTP router, REPL router, and CLI router. They all have the same type. They go from the outermost interface. So for HTTP, it's HTTP request response. REPL is a string and a string. And for CLI, it's a list of strings, which is all the arguments, and then a string out, which is std out. But what it's doing is that it's saying, I have an overall architecture, which is an outside. And this outside here goes into this type here, API or app API. And this is the bit that we're going to abstract over. And the rest is plug frontend is merely taking this and turning it into the application that will then call the database. So internally, it translates into a message, and the messages are converted into database queries, and then database queries are run. And all of this, well, all of those are different container morphisms. And what is really powerful here is that from the outside, we don't need to care about what is here. The only thing we need to care about is write this router that takes inputs from the outside and translate into messages that the app can understand. And once you've written this, everything stays the same. There's a bit more to say because you can see there's a maybe here, etc. So there's notions of monads, notions of effects, notions of monads on containers, not monads on types. There's a lot to do, a lot to work with. But it does show that given this architecture for this kind of program, you can abstract over a lot of things that are previously essentially impossible to even talk about. We can talk about programs in terms of the interfaces and manipulate those rather than talk about their implementation. And we can also modify those interfaces. Those interfaces are objects in our language. In conclusion, what we've learned is that this software can be built in a very flexible manner so that we don't need to worry about implementation details. We can talk about software in a new way. It offers an unparalleled level of abstraction because not only you can write all sorts of application, you can go as far as you want in terms of API. It will essentially not stop. I'm using this in other contexts for taking web APIs and translating to containers. You could do this for, I don't know, if you're running instrumentation or if you're running Kubernetes or any sort of tool to distribute load across servers. You could have the API across multiple servers be expressed as a container and then ahead of time be aware if you're breaking something or not. The biggest hurdle that we find is that this is only possible if you have dependent types in your languages. So if your language is only simply typed like Haskell, you will not be able to implement any of this, and you will not get the benefits of being able to tell ahead of time if your interfaces are compatible or what you need to do in order to make them compatible. And finally, because all of this is based upon a research programming language, we need to do more efforts into improving the user experience of writing this, providing better ergonomics, providing better tools, but this is what research is for. So I think I will stop here and give it back to Keith.
Thank you. Thanks, Andre. Okay, so let's wrap things up. Can this work be made accessible to non-specialists? This is important. Can this be applied by people who are technically knowledgeable, scientists, computer scientists, but are not necessarily specialists in type theory or the sort of things we've been looking at this evening? Yeah, jury's out. But I think more case studies, publications, things like that. For example, MPL will be publishing a report summarising our work. There's been a version published that's just for MPL's internal use only, but as part of this year's programme we will be publishing a report that will be available more widely on our MPL's website. LabMate, that was an interesting one. That was another part of the Trust to the Fore project that we haven't spoken about this evening, but this is taking MATLAB, beg your pardon, I've only said LabVIEW, MATLAB, I always get them confused, MATLAB, thanks for saying, and building a type system into it, one that can look at dimensions, things like that, via a series of comments, a preprocessor with comments that are meaningful to LabMate, but not necessarily to MATLAB. But that is another interesting piece of work that's for another talk maybe. So, could it be easier to make metrology accessible to computer scientists or computer scientists accessible to metrologists? Working in this sort of hinterland between these two disciplines is not the easiest place to be, but I still think it is worthwhile. So existing more unit-aware languages such as F#, which Andre mentioned, worth exploring. There are limitations, for example, with F#, as we're saying, looking at that matrix, we would be able to define units and things like that, but it would be one unit for the entire matrix, which isn't really entirely what we want. As we're looking at that previous example where dependent types allows us to look within location within a matrix and assign a type from that. And that's really kind of what would be more useful, but nonetheless, existing unit-aware languages worth exploring. So, yeah, there's value. Has been for years, has been right from the start, as I say, going back to the days of Alan Turing and Christopher, moving forward a bit to Christopher Strachey. I think MPL should just not be a passive acceptor of these tools in these languages, in terms of AI and things like that, or the theory. Okay, maybe the kind of days where things were as dramatic as they were in the 40s to the 60s or whenever, okay, those days aren't like that now, but nonetheless, we should be involved with organisations such as BCS, FACS, that kind of thing, the universities, our collaboration with Strathclyde, pushing things forward, helping shape the future. Okay, Functional languages, all right, it's probably unlikely we're going to be writing software that will be used to generate calibration certificates using Haskell or Idris. Maybe one day, but no, I think, but possibly it could have use as prototyping tools, verification, validation, alternative to MATLAB, which is probably the main use for that these days. Though, of course, Python is sneaking over. Ontologies, that is a really big and really important area for us. And that very much crosses over into theory, or I think just an appreciation of this stuff that anyone has. Knowing a little bit about the lambda calculus, lambda expressions, things like that. You'll be a better programmer for knowing that sort of thing. It's, you know, a powerful tool to make code more concise and readable. And then, of course, there is the whole question of Python, that we're now getting generations of programmers that are now being introduced to the whole concept by languages that have fairly loose, free and easy type systems. Is that a good thing? I don't think it is, but am I being too uptight about these things? Is it going to be an issue? I don't know. What do you think? I think it could be, and that's why it's nice exploring things like theory and functional languages and stuff like that. I think that's a good thing to do. Like I work in the office. And finally, these are the projects that work, as well as this year's National Measurement System project for 2024-2025. Thank you to our colleagues, Nick, for his help and guidance with the resistance calibration example. Peter Harris, Louise Wright, Ian Smith, the Science Department, Neil Garney, and of course, Colnett and Frederick at Strathclyde, and our colleagues in the gas measurements group. And there are some references, but I will supply that with a version, that I will supply to the BCS. Be down here. Okay, let's
Thank you very much, Keith and Andre. Any questions? Perhaps we'll start with questions locally, but anyone who wants, online, you can either type a question or we'll give you a chance just to unmute and ask a question.
Yes, you said using the functional languages as prototyping tools and not actually writing software in them. Why like that?
I think we still have a reasonable way to go for acceptance and use of these tools. Libraries are important as well. So, you know, there's a lot that's been done and there's confidence in them, but it's a different way of thinking. Ideally, yes, I'd like to, but plus there's also things like user interfaces and that kind of stuff, the tools for creating that. That can be a challenge, but at least introducing it and getting these ideas in there and getting things, so it's almost like baby steps, one step at a time. But yeah, ideally, yes, they would have an important role to play, but from the point of view of the practicalities and acceptance, and have to sort of baby steps that way, I'd say.
There's another aspect to it, which is functional programming languages, when they are specialized to one thing, are a good prototyping tool to do this one thing. And so there are aspects of software that greatly benefit from those aspects of functional programming languages and not others. And if we look at a language like Python, one of the reasons it's gotten useful and it's still very popular, it's more and more popular today, was because it was specialized as a prototyping tool to begin with very specific tasks. And it turned out that those tasks became more and more common and more useful, and people stuck with it, whether it was the right choice or not. So by focusing on specific aspects of the language, specific tasks, I think we can ease the use of functional programming languages and also ease the adoption of functional programming languages for larger purposes.
Okay, thanks.
Any other questions?
I suppose I'm probably going to ask some really stupid questions, but I understand the thing about going for functional programming because it looks nice, it's much closer to the maths that you're basing it on, but they tend not to be very good with typing, as you've sort of highlighted. I wondered whether you might be better off using a language that actually had some kind of concept of differentiating between types, and functional languages tend not to be. And the same with Python. I mean, it's got most loosest sense of typing you could imagine. And it seems to me that you're really sort of focusing on the different types. You don't want to sort of introduce errors by sort of mixing the sort of SI units in the wrong way.
Exactly, yeah.
And so going to functional programming just seems like you're just opening up almost infinite possibilities to really just kind of like almost everything you do, it's going to be quite hard. I mean, I don't know whether it would work because I'm not, again, I'm sort of pretty, sort of haven't looked at functional programming for a long time, but the way you're doing it, can't you just carry things around as an ordered pair where you have the value and the
No. So you can do this, and there are libraries in Python that do this, and that does work, as in it does catch some errors.
Yeah.
But that's not what we're trying to achieve here. When we say safety, it means that the error cannot happen in the first place. It means that it's not like the program is going to crash if something goes wrong. It always will. It's the program that will crash cannot even exist. That's what we're trying to build.
okay.
And functional programming, so something I would like to mention about functional programming is that the relationship is, at least for me, in reverse, as in functional programming is not magical, is merely the tool that allows to achieve this level of safety. If other tools will allow it, and there are other languages, other frameworks that allow you to obtain other guarantees, then we use those as well. It just turns out that for the specific goal of safety by design or safety by construction, like we call it, all the programming languages that exist are based upon functional programming. And it's the opposite. It's not that they're not good with types, it's that the types come first. And then given a type system, what is a good language for this type system? And almost always those languages turn out to be functional programming languages. So Haskell, F#, Idris are all functional programming languages because they implemented type theory that requires a functional programming language behind it.
I suppose the issue is that the incorrect program won't even compile rather than crash at runtime.
Yeah.
Yeah, I assume that's what
That's the whole kind of underlying concept.
So I have a question about dependent types themselves. So based on my understanding, the use of a type system is that they sort of constrict the inputs and outputs of a function, so you can reason about it more efficiently. But when it comes to dependent types, as in the value of one of the inputs can change the type of the output or something like that, wouldn't that make type systems a lot more complicated? As in you can't even check anything about them at compile time?
That's why Idris 2, for example, and Agda for that matter, and Cog for that matter, or Rock now, have constrained about what you can write in the first place. So you make the point that it makes type checking difficult. You could argue that it makes type checking undecidable because it makes it so that you now are running programs in your type checker. The obvious way to get out of this is that we require every program to be total, decidable and total. And there's an infinite amount of debate about, is that still programming, or is this still Turing complete? Can you even program with this? And the answer is yes. The Idris 2 compiler is written in Idris 2. This library that does take requests in databases, queries, etc., so is all written in Idris 2. And it is mostly total. There's only one escape hatch, which is a REPL or a server has to be written as a partial program that can crash. But the solution for this is to say, well, those programs are not allowed to exist in types. They're not allowed to exist or to be used by the compiler when they're compiling. And so this is how you make the separation between type checking is now undecidable, but if we constrain to only decidable programs, then type checking is fine. And you can still write undecidable programs outside, you're just not allowed to cross this boundary.
One language you haven't mentioned is Mathematica, so which is a functional programming. I'm sure there's issues with types that you thought about.
That is why we're not using
That's why you're
Mathematica.
not using it. It's fair enough. So you crossed it off. It's quite nice otherwise. But, yeah. Any more questions from the floor here? If there's any questions online, do just unmute yourself and say hello.
Yeah, can I pick up on one of the points you made on one of the slides about more types provide more safety? Is that because the types are more specific and therefore you can be more rigorous? And then does that conflict with the concept of reusability and making things generic rather than specific?
Both of those are right. So more types provide more safety in the sense, I wrote this a bit quickly because it's actually very subtle, but what I mean in particular is that you can be more specific. For example, for the case that Keith showed about vectors, you can be saying, well, this vector has to be exactly this length and none other, and therefore it is impossible that we'll get a data of the wrong length. That's one aspect where more types means more safety. But there's another one, which is not only you can express what the data looks like, you can make statements about them, you can prove facts about them. We've not gone here in this talk, but dependent types or dependent type systems are also theorem provers. So you can start writing theorems saying the data that we'll take in is a group. So this operation has to be reversible, and therefore it is impossible that we'll be fed in this interface something that is not a group, because the user will have had to prove that every operation is convertible. And all this aspect of theorem proving also increases part of safety, because now you can say we only know we're only ever going to deal with things that are proven to be correct or things that are within the framework that we know is true. And it does come indeed at the cost of genericity or like flexibility, because sometimes you get so precise that, well, you can't say anything wrong, but you end up in the case where you can't say anything at all. And that's problematic. So it is a skill to now, a new skill to have to learn, which is also why you mentioned usability. Again, I feel like this is more of a social problem that we need to teach people, that there's a trade-off between precision and expressivity, or precision and being usable. And at Strathclyde, we have tons and tons of code that is both extremely generic, but extremely precise too. And it's finding this right balance that is a skill that we develop over there. But indeed, it is also not a question that you will have to ask yourself in general when you work in a programming language that doesn't have this level of, this gap between so precise you can't say anything or so generic you can say anything.
Thank you.
I have a question about the adoption side. So obviously for metrology use cases, safety is very, very important. And you mentioned that, due to user interface and whatever issues, adoption is relatively low in functional environments for this kind of use cases. But then F# runs on the CLR, so you can use your existing Visual Basic tool to only have the mission critical measurement transformation functions in F#. So why are you not approaching it from that side?
That's a good question. And again, one of the whole points of this project is explore precisely those sorts of issues. And that if that's such an approach, there is value in it, then to sort of head in that kind of direction. But as I say, it's what we're having to look at these days, that a lot of people are coming at from the Python, a more loosely typed point of view. So what we're trying to do with this work is kind of publicise the fact that, there are other approaches. And that's important. But yeah, that's an excellent point you raised.
From my point of view, because I was working on this, I was already in this camp, right? I was like, you already have Windows, you already have F#, just use it. But it's a matter of like communicating to people, look what you can do, look what's possible, look how much easier to do this without having to worry about all of that. But then there's another realm of usability that is, well, now I have mission critical F# code. How do we interact with my Python code? And then people have to think about package manager. People did not use Git until a couple of years ago at NPL. So this is the kind of like bringing people up to modern practices that we have to do. This is part of this work.
Look, it is used very heavily these days. It's certainly,
Yes, thankfully.
There's a couple of years, I'd say, but definitely
There's still no package manager.
But no, it's us scientists have sort of seem to engage with Git in a way that Subversion and things like that, though people who used it, but it never really Scientists seem to like Git, and that's good. But yeah, again, raising the point about F#, and again, this was something we were just exploring ideas and returning to the point that F#, you know, you've got a matrix, that's the type, that's it. But with dependent types, we can drill down a little bit, and that's kind of a fun idea to want to explore, and that's really what this.
The F# is better than nothing.
Absolutely, yeah. From the point of view actually creating metrology software, that is an excellent point you raise. Also within this project, we just sort of with Strathclyde, because we're working with world experts on this topic, so let's have a look at these ideas and see what it can bring us. But yeah, your point is an excellent one.
Any more questions? Okay. We have a question online. I'm not a Python programmer, but curious about its efficiency. Can anyone tell me how long does it take to do 10 times 10 inverse matrix on your laptop? It's an open question.
I'm not a Python programmer, but I know how Python works, and I will tell you this depends on how you're using it. So if you're doing it through NumPy, it's going to be really fast. Yeah. If you're doing it manually yourself, it's going to be really slow. Okay. That's the answer.
Yeah. There you go. Yes. Anyone is welcome to type in another answer.
Exactly.
Please do. We've tried programming it.
Any more questions online? Questions here? Otherwise, we can say thank you very much again for